Dear students, another example on the natural convection we will take up. So here we can see that my hand symbol, whatever it is there, just follow that symbol. A vertical cylinder of 1.5 meter high and 180 millimeter in diameter is maintained at 100 degrees centigrade in an atmospheric environment of 20 degrees centigrade. Calculate the heat loss by free convection from the surface of the cylinder. And here you can see that calculate the heat loss by free convection from the surface of the cylinder. Assume the properties of the air at mean temperature. Rho is equal to 1.06 kg per meter cube. Mu, kinematic viscosity, 18.97 into 10 raised to minus 6 meter square per second. And specific heats are given 1.004 kilojoules per kg degree centigrade and thermal conductivity 0.1042 kilojoules per meter hour degree centigrade. All this for air, it is for the mean temperature. For example, if these values are not given in the given any problem, what we have to do? And what we have to do is the surface temperature is 100 degree and the outside environment temperature is 20 degree. So 100 degree plus 20 degree means 100 plus 20 degree is 120 degree and divided by 2 is 60 degree. For the average 60 degree, we can get all these value from the data book, that is heat transfer data book. So once again, I will tell, it is a vertical cylinder, 1.5 meter high and 180 millimeter in diameter. Vertically it is placed and is maintained at 100 degrees centigrade at an atmospheric environment of temperature 20 degrees centigrade. So average temperature means 100 plus 20, 120, 120 divided by 2 is 60 degrees centigrade. Film temperature is 60 degrees centigrade. Calculate the heat loss by free convection or natural convection from the surface of the cylinder. Assume the properties of the air. Density of the air is 1.06 kg per meter cube. Kinematic viscosity is 18.97 into 10 raised to minus 6 meter square per second. Cp is equal to 1.004 kilojoules per kg degree centigrade. Thermal conductivity is 0.1042 kilojoules per meter degree centigrade. All these are already given, so it is facilitated. But not that if they are not giving the values, then you have to go for average temperature. 100 plus 20 divided by 2, that is 60 degree. It is available in the data book. So they given all the values they have listed. Length is 1.5 meter, diameter is 180 millimeter, converted to meter 0.18 meter. Surface temperature is 100 degrees centigrade. Surrounding temperature is 20 degrees centigrade. Density, kinematic viscosity, specific heat, and thermal conductivity all are listed here. So first and what we have to do is heat loss by free convection, that is Q. Heat loss is what. So first we have to calculate the dynamic viscosity. Dynamic viscosity symbol is mu, that is density into kinematic viscosity. At the bottom of the heat transfer data book, you can find that equation. Okay, whenever you open the page for the properties of the air, only kinematic viscosity in some cases will be given. So you have to multiply with the density, so we will get the dynamic viscosity. So dynamic viscosity is equal to density into kinematic viscosity. Simply we have to multiply 1.06 here and 18.97 into 10 raised to minus 6. That is there. Okay, so why it is multiplied by 3600? Because to match with the hour parameter. Where is our parameter? K is equal to 0.1042 kilojoules per meter hour. So that to have the uniform or homogeneity in the units, what they have did is they have multiplied by 3600. Don't get confused about it. You can keep in seconds, there is no problem, or you can convert this hour into seconds. Both you can do. So what they have chosen is they have chosen to convert it into hour itself. Okay, 0.07239 kg per meter hour. They have multiplied by 3600 to have the homogeneity with the other parameters. Beta, coefficient of thermal expansion, 1 by T. So T must be, temperature must be in what? Kelvin. I already told that the temperature should be always in Kelvin for coefficient of thermal expansion. So 1 by 273 plus film temperature. 273 there plus 120 plus divided by 2. 120 plus 2 divided by 2 means 27 plus 60. That is 0.003 Kelvin per Kelvin. It is there. So Grashoff's number we have to find out. Grashoff's number L raised to 3 G beta delta T and nu square. This is whether you have to by heart or this is available in the data book. Don't need to worry about it. So length of the cylinder, length raised to 3, so 1.5 meter. Here you can see 1.5 meter. Then 9.81 G, beta is 0.003, and temperature difference is 100 degree minus 20 degree. So temperature difference is 100 minus 20 degree. Divide by nu, it is not V, it is nu, that is kinematic viscosity. Kinematic viscosity is available 18.97 into 10 raised to minus 6 brackets, that is square. So it amounts to be 2.208 into 10 raised to 10. Then we have to go for Prandtl's number. So Prandtl number is mu Cp by K. Again, this equation is available in the data book. But you have to check it and find the place where it appears in the data book. That is very, very important. Okay. Don't search in the examination. So naturally what happens, mu is there, that is dynamic viscosity 0.07239 into Cp. See what is Cp? Specific heat 1.004 kilojoules per kg. And thermal conductivity is 0.1042 kilojoules per meter hour. So it amounts to Prandtl number amounts to be 0.6975. Okay. So here we can have so we'll scroll to the other side of the section. So now you have to multiply Grashoff's number and Prandtl's number. So Grashoff number is 2.208 into 10 raised to 10 and Prandtl's number 0.6797. So multiply it is 1.54 into 10 raised to 10. These are all numbers. So therefore Grashoff's number multiplied by Prandtl's number, if this value amounts to be in the turbulent range. Okay. So greater to in the form of 10 raised to 10. So what will happen? This will value for 10 raised to 9 to 10 raised to 12. So for that, this equation is there, and this is the turbulent range. This turbulent range is also available in the data book, in which range it falls. The multiplication of Grashoff's number and Prandtl's number, it lies between 10 raised to 9 to 10 raised to 12. So in this case, it is turbulent range, and the corresponding equation for the turbulent range is this much. What is that? Nusselt's number. Nusselt's number for the full length, HL by K. HL by K is available in data book. That is also there. But remember it, better to remember it. 0.10 Grashoff's number and Prandtl's number product raised to 1 by 3. So 0.10 as it is, and the product of GR into PR is 1.54 into 10 raised to 10 raised to 1 by 3. That is 248.75. So then what will happen? H is, so Nusselt's number is equal to HL by K. So H is equal to KL into Nusselt's number. Same equation. This equation are same. So we have to find out H, that is convection heat transfer coefficient H. So K by L, K is 0.1042, L is 1.5 into 248.75, that is this much value, that is 17.283 kilojoules per hour meter square degree centigrade. So here, this is all we have in search of H, that is convection heat transfer coefficient, because we know that the Q, that is range of heat loss or the heat loss parameter, can be calculated just one simple equation, HA delta T, basically HA delta T. H is convection heat transfer coefficient, A means area participated in the heat transfer. Remember that in the conduction, it is the perpendicular cross section we have to use, and in convection, the area which is actually participating in the heat transfer process, that area you have to take. So Ts minus T infinity, surface temperature of the object minus surface temperature of the surrounding. So H on an average H is 17.283. So the area, surface area which is participating, it is a vertical cylinder. So cylinder is there with surface area is pi dl, pi into 0.18, that is the diameter in meter, and L is length 1.5 meter. Into 100 minus 20, object temperature minus surrounding temperature, that amounts to be 1172.8 kilojoules per hour. This is the range of heat loss. So an object, if a hot body kept in a vertical position, how it loses the heat? In what way, at what rate it loses the heat, that we are calculating. So frequent use and most important is up to this point everything is okay, but this particular point where product of GR and PR, whether it falls in laminar range or turbulent range, you have to find out very carefully. Visualize the particular number And in the data book, you can have for different range, different equations are there. Sometimes many equations are there. Most widely used these equations you have to use for this particular range, and you have to identify the range. This range is turbulent range. And here, and then you have to go for range of heat loss. That is very, very important. Means the student who is well acquainted with the heat transfer data book will excel in the academics. Again and again, I am telling this factor. Thank you.